Okay, thank you so much. There was a, it was a rough start, but it's better than nothing, right? Okay, let's officially start. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker today, let's go over some rules and logistics as usual. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences, so no classified discussion is allowed. Please watch out. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Professor David, who is a professor in Mainz, ParisTech University, and the head of the program, PhD program in mechanical engineering. He has coined the word hyperreduction in reduced order model community, which is very crucial, especially for nonlinear dynamical system model order reduction. And he also did seminal work in a priori model reduction. And he was the head of the research team involving 12 permanent researchers at Mainz ParisTech from 2011 to 2015. His current research focuses on model order reduction, multi-physics modeling of thermomechanical processes, and inverse problems. Okay, today David will present model order reduction assisted by deep neural network, so-called ROMnet, which is a great interest to us. So please enjoy and expect a wonderful talk from David. Now, without further ado, let me pass the baton to David by asking one random question. Today's random question is, what's the smartest thing you've ever done in your life?
Oh, oh, it was the birth of my first daughter.
Yes, of course. How many kids do you have?
3.
Oh,
2
I
girls
see.
and 1 boy.
Yeah. I see. Of course, yeah. I knew that was the answer. Okay, it's all yours, David.
Okay, thank you, Young Shol, for your kind invitation for this seminar. And it's great for me.
Make sure share your screen.
Yes.
Yeah.
So, do you see my presentation here?
Yeah, but it's not full screen. Can you make it?
So now it's full screen, I think.
Yes.
Okay, so I would like to talk about model order reduction assisted by deep neural network, and it's termed ROMnet. So at School of Mines, we are working on digital images on materials, and we try to make digital twins of these images. And obviously, we need deep learning for various interactions between images and machine learning, or between machine learning and finite element model. I would like to explain that through this presentation. So I'm going to talk about ROMnets developed during the PhD thesis of Thomas Daniel, and this research was funded by Safran. So what are the motivations? Why there is 3 interacting disciplines in my logo? There is 3 main factors promoting the development of machine learning for engineering application in mechanics. First, material imaging made huge progresses in terms of resolution, but also thanks to the development of X-ray tomography. And X-ray tomography can capture the 3D morphology of various kinds of metals and composite materials. Second, such observations can be used to feed numerical modeling in digital twins, but also in various physical models. And today, supercomputers are available in order to make huge simulation, especially finite element simulation. And on the top of that, machine learning, especially for image transformations, has become more efficient and robust these last 2 decades, and both for supervised and self-supervised learning tasks. And we all know that Python libraries are freely available. So for all of that, today it is time for the interaction of these disciplines to develop engineering tasks assisted by deep learning. In aeronautics or in many other industrial sectors here, engineers have to design or exploit complex systems where decisions are supported by numerical models. This is termed model-based system engineering. Complex systems, in fact, are systems that require model-based engineering. These models have an informatic representation here on specialized informatics platforms. In these platforms, we find workflows that connect CAD to finite element solution of partial differential equation. And when the simple numerical models are available, one can run uncertainty quantification for robust optimization purpose or for decision making. The ground truth here for uncertainty quantification comes from observational data, especially those related to manufacturing processes. But uncertainty can also come from complex environment, and like in a multiphysics problem. So I would argue that data in engineering is valuable as much as it is in healthcare, for example. Thanks to the experience of most people in the audience today, we know that storing data can save time if we use machine learning. This opens new opportunities for more uncertainty quantification and robust optimization. Such tasks are still very hard to perform on complex systems, especially since the source of uncertainty are increasing with the improvement of imaging techniques for engineering. The role of images in numerical modeling will certainly grow in the future. Here it is an example of X-ray tomography of defects in a welding joint. In image-based models, images are input parameters for numerical models. And these parameters are denoted by mu. They are physical parameters. The parameter space or the ambient space for images is so huge, then dimensionality reduction makes sense for both parameters like images as well as simulation data. We obviously adopt the data-driven modeling approach. In practice, during the design of complex systems or during their exploitation, the parameter space is sampled many times. Similarly to physics-informed neural networks, data-driven modeling for model reduction aims to make the best use of existing data while exploiting the information from classical mathematical model. In my point of view, we can achieve this kind of learning by transfer learning. We will see that later in my talk. But in engineering science, we seek for interpretable models. And it is a very difficult topic in machine learning. Model-based engineering are 100% interpretable, but sometimes too deterministic. Global interpretability in machine learning describes the overall features that mostly contributed to the model's performance. And local interpretability works at the online step and represents the features that contributed to a specific decision for a specific input. We need both in engineering. Let's talk now about the simulation data. So, simulation data are produced by numerical solution of partial differential equation. The solution of this, the solution of this partial differential equation is denoted by U. And this solution is parameter dependent because the partial differential equation L is parameter dependent. It is depending on mu. So the solution is both defined over a spatial domain denoted omega and over parameter space P. Here, the matrix X is a storage matrix of simulation data. Each time we sample the parameter space, we get a new parameter mu I. And we put this mu I in a row of the matrix X. Here, the idea behind data-driven modeling is that the row of X, the rows of X, do not fill up the entire embedding space. The data are solution of the PDE, and they are living on a latent space. I would say a true latent space. This is the green curve here, and it is sampled by blue points each time we solve the partial differential equation by using a finite element model. The finite element model has a residual R, and it has a vector of degrees of freedom Q. Each time we do a simulation, a finite element simulation, we fulfill this equation, the residual equal to 0, and this defines the true equation of the true latent space. So in fact, we exactly know the equation of this latent space. For a finite element model, the solution of this residual equal to 0 is very expensive, it is too long, and we want to get a simpler equation for the latent space. For example, one of the target applications for ROMnet is the thermomechanical simulation of a turbine blade. In this blade, the temperature field is a random variable, and it is an input variable for the mechanical problem. In the mechanical problem, it's an elastoplastic problem with the finite element method. So we have finite element shape function and nodal degrees of freedom Qj. And in this kind of example, we have 15 millions of degrees of freedom. And the solution for 100 loading cycles takes 300 days to get the plasticity inside the blade. So it's very complex simulation, and we would like to find a reduced latent space for that kind of simulation. So here we are using universal approximation theorems of feed-forward neural networks to get reduced equations for the latent space. We seek for data-driven approximation by using an approximation space, VL, as a subspace of the finite element space. So ROMnets are using projection-based model order reduction. Why? Why not using metamodels and regressions via supervised learning? As I said earlier, projection-based model order reduction enables a kind of transfer learning. In that transfer learning, the source domain is computational mechanics. The target domain is fast parametric predictions using machine learning. The knowledge encoded in PDEs is reused in a nonlinear scheme for projection-based model order reduction. Thus, machine learning is only focused on a few physical parameters. We don't have to rediscover all the equations of physics. So we are focused on a few physical parameters, but they are highly dimensional ones, like images, for instance. So we are using machine learning. We need to train models. So for that, we have a training step, also termed offline step, and it starts with a numerical simulation according to a sampling of the parameter space. Thanks to that, we can arrange the simulation results in the rows of matrix X. Usually, X has much more columns than rows. So we have a very big fidelity model that know very well the knowledge in physics, and we run it to get simulation data, and it ends by a reduced order model that speed up simulation. Dimensionality reduction belongs to manifold learning methods. The reduced space is a data-driven latent space that aims to retain some manifold properties of the original data, ideally close to the intrinsic dimension of the true latent space. Note that manifold learning is fine for data visualization, but here we need equations for the reduced latent space. The coordinates in these equations are termed reduced coordinate. So I would like a question. I would like to ask a question. Maybe you can reply to it by using the chat, but unfortunately I don't see the chat. But what is the linear latent space when all simulation data are aligned? What is the term for that in linear algebra? Certainly you know that. Usually, linear latent spaces are well known for model order reduction. They are very interesting, even if the finite element model is nonlinear. The linearity of the latent space and the linearity of the finite element equations are two different things. So the answer to the equation is a linear latent space. Use these linear equations, so it is a vector subspace of the finite element space. In the cycle, the reduced coordinates on the reduced latent space, the reduced coordinate z, are a vector of dimension n, very small compared to curly n, the number of degrees of freedom in the finite element model. And thanks to that, we have only capital N equation, so less equation to solve in order to find points onto the reduced latent space. So with smaller number equation, it should be faster. So undercomplete autoencoders are well-known neural networks for dimensional reduction of data by using a latent variable z. This is the same z. It performs a nonlinear dimensionality reduction thanks to the decoder. These neural networks are trained by self-supervised machine learning. The output must be equal to the input. And the projection-based reduced order model using decoder of autoencoders have been proposed by Lee and Karlberg last year. In this approach, a minimization of the finite element residual R is performed by using the decoder of the autoencoder. So here, thanks to this minimization problem, we can find the best reduced coordinate, and we obtain thereafter the estimation of the degrees of freedom Q. So we have less variables, but they are more nonlinear because of the nonlinearity of the decoder. If the activation function in the encoder and decoder are the linear function, and if we use two fully connected neural networks, we obtain a linear equation for dimensionality reduction. We obtain linear dimensionality reduction. Therefore, X equals Z times the decoder V transpose. And the decoder V must be obtained by solving an optimization problem. The solution of this optimization problem is given thanks to the Eckart-Jung theorem, and it is the SVD decomposition of matrix X that gives the best decoder V. So a linear encoder gives Z equal to X times V, and the decoder X approximated by Z times V transpose. So in model order reduction, we use Ryckelynck projection. And we need to introduce for that the reduced approximation space, VROM, that use the linear decoder, V times Z transpose. This is the transpose of the previous equation for linear algebra. And the Ryckelynck projection reads this equation. It is the projection of finite element residual onto the subspace spanned by the columns of V. So each time we have a parameter mu, we can find the Z thanks to this linear reduction approach. And we can see that the reduced order model here is a supplement to the decoder in order to describe the point Z onto the latent space. So we know, most of us know that Galerkin projections do not reduce computational complexity sufficiently, because here the computation of the residual, finite element residual, scales with the number of degrees of freedom curly n. So if we are using hyperreduction, we can reduce this complexity. For instance, we can use a reduced integration domain for that, and therefore it is a selection of few residual, finite element residual, in order to obtain this projection. And the purpose of ROMnet is to extend this to nonlinear model order reduction. A key idea for that is sparse dictionary learning. Sparse dictionary learning allows redundancy in a dictionary of empirical vector. And in singular value decomposition, the loss function is a two-norm function between the input and the output. It is the two-norm of the discrepancy between the input and the output. And this is fine for linear autoencoder. But in sparse dictionary learning, the loss function contains L0 and L1 penalization terms to enforce a sparse representation of the latent variables. Sparse dictionary learning can be understood as a piecewise linear latent space in some situation. Let's consider the case of K clusters of data in X. We have K cluster of data, and for each cluster we can use the K SVD in order to get for each cluster a proper reduced basis thanks to the local SVD in the cluster. So it is a kind of sparse dictionary learning, and it is very interesting because it gives a piecewise linear reduced space, and this enables the hyperreduction. It is very straightforward to apply hyperreduction. In that case, this has been proposed, for instance, by using the local die. In addition, sparse latent space are desirable for interpretability. When the parameter space has a huge dimension, it makes sense to define categories of data. For example, for the assessment of defects, of harmfulness of defects, the category of spherical defect and the category of penny-shaped defect can make sense. So using clustering strategy can help for interpretability. And for this reason, I think, this is my opinion, that ROM dictionaries are very interesting for interpretability. Maybe they have a better interpretability than autoencoders. So what is a reduced order model network? A ROMnet is a feed-forward artificial neural network that ends with a reduced order model via a projection-based model reduction. It is designed mostly for image type parameter as input parameter for the nonlinear model order reduction. And it aims to perform an approximation of the latent space by using a piecewise linear reduced space. So we need to train cluster of simulation data prior the construction of local reduced basis per cluster. And this clustering procedure enables to adopt a goal-oriented metric for that clustering. The goal-oriented metric is the Grassmann distance between vector subspace. This Grassmann distance measures the angles between two reduced bases. Here, we replace simulation data in the finite element ambient space by reduced basis. Each point is now an ideal reduced basis. Each simulation is transformed, thanks to the SVD, into a reduced basis for an ideal reduced basis, and this ideal reduced basis is the best reduced basis for the simulation. So this V star I is the best reduced basis for simulation I. And the Grassmann distance is the angle between various reduced bases, between two reduced bases. And therefore, we obtain a matrix of Grassmann distance between all the simulation data in this ambient space that look like a circle. And thanks to this matrix, we can train a k-medoid algorithm in order to extract medoid. A medoid is a point in the training set that is close to the center of the cluster. And so they are reduced basis, but each reduced basis being a training point, it is related to a specific input parameter mu k. And thanks to this, we get labeled data for temperature field, for instance, or for images. And then we obtain a piecewise linear approximation space like this, where the approximation space for partial differential equations is a subspace of finite element approximation space, but it uses a nonlinear model reduction because the reduced basis depends on the results of a classifier that is where the classifier takes the input parameter mu in order to recognize the best reduced basis that we should use for this input parameter. So we obtain a nonlinear reduction scheme through the classifier, but we are using local and linear projections of the finite element equations. They are local in the cluster. And so the classifier is solving the nonlinear aspect of the nonlinear model order reduction. And we still have a kind of transfer learning thanks to the finite element residual. Okay. So we can consider many target problems involving image-based modeling, but not only. We know that the ambient space for images is huge. So sensitivity analyses are not tractable to reduce the parameter space. But convolutional neural networks are very efficient in image classification tasks. Hence, it makes sense to adopt CNN as a classifier in ROMnets. In addition, fields in science or finite element data can be considered as images. This is a new paradigm to couple machine learning and computational mechanics. In the cycle, the temperature field in a thermomechanical problem is considered as an input image of a ROMnet. So this is a numerical example. In a thermomechanical problem, a stochastic temperature field is the input data for a mechanical problem, an elastoplastic problem. This problem is similar to the computation of a turbine blade. It has the same constitutive equations. And each time we have a random realization of the temperature field, we have to compute the mechanical solution of the elastoplastic problem. And we would like to use a ROMnet for that. So the training steps of a ROMnet are the following. First, the parameter space is sampled randomly, and for each sample mu I, finite element simulation generates simulation data. In order to compute the Grassmann distance between simulation data, a SVD extracts the ideal radius basis for each simulation individually. Next, the full matrix of Grassmann distances is computed between all couples of ideal radius basis. The K-medoid algorithm finds the medoids in the Grassmann manifold. Thanks to that, we can label the input thermal field according to the results of the clustering procedure based on ideal radius basis. After that, a CNN classifier is trained to learn the relation between the thermal field and the labels. Upon the results of the clustering procedure, a local radius basis is trained locally on each cluster separately. So the clustering results are the following. In this example, radius bases have two modes. We can plot the Grassmann manifold by using a multidimensional scaling of scikit-learn. And it is based on the Grassmann distance matrix. On the left, on the right, we show the results of the clustering procedure based on the distance between ideal radius basis. So we obtain a perfect clustering by using 6 clusters. If we compare these results with a clustering related to the input temperature field, we can define 6 clusters of input temperature field by using an Euclidean distance, and we can see that there is no a straightforward relation between the two clustering procedures. So this is the reason why we need a CNN classifier in order to learn the relation between input thermal field parameter and labels of a cluster. Okay. On the top right, these curves show the density probability function for intra dissimilarity by using the Grassmann distance. Small dissimilarity means low approximation errors by using nonlinear model order reduction. The red curve is the one obtained by using only one cluster of data. It is the case when we want to train a global reduced basis by using linear model order reduction. So the red curve is the one obtained without clustering. The blue curve is related to the ROMnet clustering based on the Grassmann distance between ideal reduced basis. And we can see that we reduce a lot the dissimilarity inside each cluster of simulation data. And if we use 6 clusters of temperature field, it does not improve anything inside cluster of similar temperature field. So the right metric for the latent space is given by the Grassmann distance between ideal reduced basis, ideal local reduced basis for each simulation individually. So the CNN classifier is similar to the one used in RxNet here. It has 3 blocks of convolutional layers, and we use a ReLU activation function. And here we can see the results of the confusion matrix between the true labels and the predicted labels. And the average accuracy is around 74% of accuracy. So it is quite good. And this is interesting to see that wrong labeling is not so bad, because it gives a local reduced basis that is very close to the target, to the true reduced basis. And this can be seen here on this plot here. These points are points that should be in class 0, but the CNN says that they are in class 1, but they are not so far from class 0. So it is quite satisfactory. To train this CNN classifier, we need as input thermal input, temperature input. So we transform the finite element data into an image thanks to a regular mesh, and in the thickness we are using the channels of the 2D image to set up the training data of the CNN. The final results are here. The high fidelity model has 200,000 of degrees of freedom, and the local reduced basis have only 2 modes for all clusters, and there is 6 clusters, and the simulation speedup is 60, and the error in predicting plastic strain by this ROMnet is only 5%. So this accuracy is very fine for uncertainty quantification. So there is several works in progress in my team about ROMnets. Thomas Daniel is now working on realistic industrial cases for saffron. And Hugo Launay is developing autoencoders for crack assessment. In that work, the input parameters are images of local cracks. And Pablo Pereira is working on a local reduced basis for real-time prediction of stress in a welding process. In that work, the input parameter are thermal field again. So my conclusion is new numerical methods are coupling machine learning and solution of partial differential equation. And they are going to change the working environment for engineering. And data related to fields in mechanics can be considered as tensor or images. And this is very interesting to develop image transformation upon this idea. So the step-by-step training of ROMnet with intermediate classification results facilitate the local interpretability of ROMnet results. We can check if the temperature input is similar to the medoid, and we also can check if the mechanical prediction are similar to the medoid too. And using Grassmann metrics for the latent metrics is very interesting because it's quite general approach in computational mechanics. And eventually a CNN classifier can handle non-parametric modeling. No knowledge on parameter are introduced to solve the classification problem. And this is very interesting for non-parametric uncertainty quantification. So thank you for your attention. I switch off my presentation, and if you want, I can answer to questions.
Thank you, David, so much for the great talk. I really enjoyed it. Let's have a Q&A session now. Okay, so I don't see any questions in the chat room, okay. But you can unmute yourself and then ask questions. Okay, so while you are thinking about the questions, I have questions. So
yes,
that's very a good idea to taking advantage of the CNN classifier in order to the cluster and match that with a different label. Well, what is the speed up you're getting when you compare that to corresponding full order model?
The speed up is the total speed up is 60 compared to the finite element solution in this simple case.
Okay, the thermal mechanical simulation.
Yeah.
Okay.
Yeah.
That's
in fact,
that's very nice.
we only have a nonlinear mechanical simulation with a thermal input.
Okay. That's very nice. Okay, the simulation speed was 60. Okay, I missed that. Okay, there is a question from Harshit. On slide 33, a probabilistic model for the input data is needed. Why is that the case?
So, yes, it's better because if we have a probabilistic model for a thermal field, it's easier to sample the input parameter space. So we can focus data sampling thanks to this probabilistic model. If not, it is maybe more difficult, but it is possible to sample the parameter space anyway.
Good. Okay. Thank you. Any other questions from audience? Okay. Harshi said thank you. Okay. Rahul asked, I'd like to know where the transfer learning has been implemented for the reduced order model.
Yeah. So it is a kind of transfer learning. It is not the same transfer learning as for CNN. The transfer learning here is related to the residual of finite element equation. In that residual, we have all the mechanical knowledge, for instance, about the constitutive equation, about the loading, and about the geometry of the problem. So since we are using the finite element residual, we transfer this knowledge into this nonlinear scheme for model order reduction.
Yeah, so just to add to that, you know, yeah, it's not a direct application of the transfer learning in machine learning community. It is an analogy.
Transfer learning for convolutional neural network.
Yeah, it's more the analogy, not a direct application. Yeah.
Yeah, we have knowledge, and we don't want to train neural network in order to rediscover this knowledge.
Yeah, exactly. Rahul just commented that it's not a transfer of the weights, but the transfer of the prior knowledge. Yeah, exactly. Yeah. Okay. Another question from me is some technical details about the hyperreduction on each local ROM. So I'm assuming you are applying the hyperreduction each local ROM. So when you apply that, you will end up with a different set of the collocation.
Yes.
Or for different local ROM, right? So you have to store that somewhere in the system, and then once the cluster tells you, okay, go to this cluster, you invoke those correct hyperreduced set.
So the classifier gives the cluster number, and for each cluster we have a set of data related to hyperreduction. We have the radius basis, but also the weight if you are using energy sampling approach, and we also here we are using the reduced domain, so we have to save the reduced mesh for each cluster.
Right. So okay, so all right. Raul Bravo has another question. Given that you only have 6 clusters and that each of them returns 2 mode bases, was it necessary to use clustering? What is the gaining compared to using a single cluster and therefore a single basis?
Okay. We did not use the okay. Here is the comparison. Here, so I didn't show all results, but the Grassmann distance is a kind of upper bound for elastic problem, is a kind of upper bound of the approximation error when using reduced order modeling. So the distance inside each cluster, the intra distance in the same cluster, are much smaller by using 6 clusters than by using only 1 cluster. And for each cases, we are using a reduced basis of dimension 2. It's hard to compare results by changing the dimension of the reduced basis, because it's more easier to fix the dimension of the reduced basis and to compare errors. But we can evaluate also, we can evaluate the gain in terms of accuracy. And but for this gain, we need to compare reduced basis with the same number of modes. Obviously, maybe for that problem, we could have used a reduced basis involving maybe 100 modes to account for the various effects of thermal fields. But 100 modes is a very huge basis. And I have to mention that computational complexity of reduced order model depends on the cube, on the size of the reduced basis to the power 3. Because when you are using a local reduced basis, we have to solve linear problems that have full matrices compared to finite element models that have sparse matrices. And empirically, we have to fulfill this restriction. And this means that 100 modes is very, very high for a reduced order model. So this is the reason why sometimes we need to use clusters of data and ROMnets to solve nonlinear model order reduction.
Yep. Okay. Thank you. And next question is by Beta. Is this method applicable for ODEs as well?
Sorry, I was reading the previous. Okay. Oh, I'm lost. So
it's from Beta. The next question is from Beta.
Yeah.
It's is it applicable to ordinary differential equation? Yeah, that's the question.
Yes. Yes, the basis obtained for a cluster is used for all the simulation if the classifier recognize in the input image that we must use the cluster.
Oh, well, okay. So you just answered the Rahul's question, right?
Yes.
Are the basis of okay? So thank you for that. Okay, let's go backward. Okay. It's next one is rather a comment than question. It's from the Rob Blake. He recommends to use the k-sparse autoencoders, and he also made a link for that k-sparse autoencoder.
I will see that later. Yeah. Thank you very much. Sparsity is a very interesting topic.
Exactly, in order to obtain the efficiency. Yes. Okay, the next question is Rahul's. I'm going backward. Okay, although the temporal complexity is reduced, what is the memory required while solving for the reduced order model, given that it is a parametric reduced order model?
So about the memory, it depends on the number of clusters. So it is, if we have 6 clusters, it is 6 times more memory demanding. So, but we just need to save the parameters for hyper reduction, and these parameters are saved only for reduced mesh if we need to save memory. we can use a kind of data pruning related to hyper reduction.
Okay, thank you. And answering to Beta's question, is more method applicable to ordinary differential equations? Yeah, I would say yes, but I mean,
yes, of course, yes, we did it.
Of course, yes, yeah. Okay. And another question from Rahul: the speed up is 60, around 60, so it still takes 5 days, unlike the finite element method simulation, which is of order of 300 days. So where is the maximum computational effort?
Okay.
Directed.
So the simulation that takes 300 days has 15 millions of degrees of freedom, and the larger the high fidelity model, the better the speed up. So the speed up for this, we are simulation, finite element simulation are still running for that problem, and but we expect speed up around 1,000.
Yeah, so I mean, usually visual pseudo model, when it is applied to larger scale problem, you will get the higher speed up. So that's kind of known fact.
Because the geometry is more complex, but the mechanics inside is not so complex.
Yeah, the intrinsic subspace is still small.
Yes.
Yeah. Okay. I don't see any more questions from audience.
Okay.
Yeah. Thanks so much. Okay. Thank you so much, David, for the wonderful talk and answering all those questions. I hope that, and through this seminar talk, I hope that you will be connected with many scientists in Lawrence Livermore, so that you can do the collaboration in the future.
Yes,
that's one of the motivation of this seminar talk. So
that's
I
a
hope
very
that,
nice idea.
Yeah, I hope that it's going to happen. Okay, thank you so much. Let's applaud for great talk for David.
Thank you.
Thank you so much. And I'm sorry again for the rough start today, but I guess we did manage to finish the seminar, without any hassle. Except the beginning part. Okay, thank you so much, everyone. Yeah, thank you so much for everyone.
Thank you. Bye.
Okay, we will see you in next DDPS seminar. Okay, bye, everyone.